I think it's time to start. So it will be Antonio Rubio Abadal of the Max Planck Garching about Manybody localization. You will have, where is it? My time is 15h40. Okay. So it's 30 minutes plus questions. And are you ready, Antonio?
Yes, I'm ready.
Okay, we can see you clearly. Hi.
Hi. Can you hear me too? Or?
Yes, absolutely.
Perfect.
So I think you can start. And let's say after 25 minutes, I will give you a warning. Okay?
Perfect. Yeah. So let me thank the organizers of this summer school for the invitation, and also all the previous speakers for already introducing many topics that will be useful for my talk. So I'm from the Max Planck Institute of Quantum Optics, from the group of Immanuel Bloch, and I will talk about some experiments that we did in Manybody localization on the disorder Bose-Hubbard model. And I'd like to begin by motivating this from a bit of a different perspective, and in particular that of quantum thermalization. And the question is, how do isolated quantum systems thermalize, and whether they do? And from the point of view of ultra-cold atoms, this has been explored in many kinds of experiments. For example, Jörg Schmidt-Meyer has looked at many of these questions with one-dimensional Bose gases. Also in the group, in our group, there's been experiments looking at the relaxation dynamics of some initial density pattern, like this experiment a few years ago. And for example, in the group of Markus Greiner, there's also been experiments with the quantum gas microscope, looking at, again, dynamics in the Bose-Hubbard and how unitary dynamics can nonetheless lead to some kind of local thermalization of a system, right? And in general, when one has such phenomena, one tries to look at exceptions of this quantum thermalization, and integrable systems have emerged as one of those. So this is an experiment also in 1D Bose gases, the so-called quantum Newton cradle, in which after a kick in momentum of this 1D Bose gas, it was observed that it did not relax to a thermal state. But these kind of integrable systems typically are so-called fine-tuned, in the sense that getting out of integrability can easily restore thermalization. And this was actually done very recently in the group of Ben Lev in Stanford, where they looked at these prosium atoms which have dipolar interactions, and this actually was able to restore thermalization in the system. But of course, another different kind of systems, which again goes much more into the direction of what we're discussing this summer school, is the Anderson localization, as these beautiful experiments of matter waves, like in Institute Optique or in Florence. But again, in a sense, they are fine-tuned in the sense that it's mostly focused in the non-interacting regime. So one might wonder, can we find exceptions to this thermalization also in generic systems? And this is a bit how we come to the topic of Manybody localization. So typically one can get here by, as many have asked in this conference, what is the fate of Anderson localization when we introduce interactions? But one can also get here asking just, are there exceptions to this process of quantum thermalization in isolated quantum systems? And again, the answer to both questions can be found in Manybody localization, which can be defined as a failure of quantum thermalization for a closed quantum system at high energy densities. So not only in the ground state, but also in any eigenstates at finite energy density. And it's a generic system in the sense that there's a lot of models involving just interactions and quench disorder, and small perturbations might still keep this behavior. Now, of course, for experimentally, there's been, and already Thierry introduced some of these experiments that were done, for example, in Florence, in which they looked at disordered and interacting system in optical lattices. And also a lot of works have been done in the group of Brian DeMarco in Illinois. But in a sense, what we'd like to focus more on this talk today is in the introduction of a quench and looking at dynamics of some properties of the system as a function of time. And Uli already mentioned some of these experiments that were done with ultra-cold atoms in the Fermi-Hubbard model with quasi-periodic lattices. But recently, there's been also a lot of interest for these questions on Manybody localization on a lot of other platforms, in particular trapped ions, like in Chris Monroe's experiment, superconducting circuits, like in Santa Barbara and also Beijing, and also NMR systems like this from the group of Paola Capellaro. And I just wanted to, before starting, summarize some of the different properties and advantages of each one of these platforms or different setups. For example, in observables, many experiments focus on the dynamics of initial conditions, like for example, the imbalance of some initial density pattern. But there's also been experiments looking at density correlations and Renyi entanglement entropy. For example, if you follow the quantum science seminar, Peter Zoller was talking about this yesterday. And also spectral signatures, which are available in systems of superconducting circuits. So, and concerning dimension and the size of the system, well, there's been most of the work in 1D, again, both in ultra-cold atoms and trapped ions, like these examples. But also recently, there's been a lot of experiments in 2 dimensions. For example, this is, again, the Fermi-Havard experiment in the University of Munich. And this is our setup with a bosonic quantum gas microscope. And actually, very recently, Google also started using this Sycamore setup to study such kind of questions, also in 2D. But the sizes of these systems can vary largely. So for example, these were systems of 12 lattice sites in 1D, while the experiments in this Fermi-Havard, they usually involve hundreds or even thousands of atoms. So in general, ultra-cold atoms have the advantage that it's easy to scale to large atom numbers for study these kind of systems. And at the same time that they have a high level of isolation, which allows to go to very long tunneling times. And the short outline of my talk will be, I will introduce our setup, which I refer to as a dirty boson quantum gas microscope. I will show some results on thermalization and localization in 2D. And last, I will mention a recent result on introducing a quantum bath. And please interrupt me at any time if there are questions. I'm not able to see the chat, so I hope, Alan, you can just let me know.
I will try.
So
and if I don't, other people can.
All right, perfect. So just to put things in, this is experiments that are done in the campus of Garching, north of Munich in MPQ, and it's a so-called rubidium-87 quantum gas microscope. And our system begins with the creation of a 3-dimensional cloud, of degenerate cloud, that we load into this vertical optical lattice. And by using some tricks, we're able to just generate a single 2D pancake. Additionally, we add these optical lattices in the plane, generating, which can be described by a 2D Bose-Hubbard. Now, the main feature is that we use fluorescence imaging. So we take the lattices at much deeper values than the ones in which we do physics. We then scatter thousands and thousands of photons. We gather all of them with a high NA objective. And this allows us to obtain pictures like this one. And this does not really correspond to a cold cloud, but rather a pretty thermal one. But you can see those white dots just represent the lattice antinodes, and that in some of those are occupied by atoms, and that the light coming from those atoms has this kind of point spread function. And when they are very close, we cannot really resolve them well. The light coming from them overlaps, but knowing that we have an optical lattice, it's easy to reconstruct with high fidelity their occupations. And usually we don't work with this kind of system, but we work more with a close to unit filling Mott insulator in the atomic limit, which in some of our best days, it looks like this. In fact, here there's only a single defect in the center, which you can see in the reconstruction. And this is most likely a doubly occupied site, since our system can only distinguish the parity, so even or odd occupation in each individual lattice set. Now, the objective can be used not only to observe the atoms, but also to manipulate their state. And together with a digital micromirror device, which allows us just to program arbitrary patterns for the light that we project on the atoms. And this is used both for single site addressing and to generate physically relevant patterns like this one of the atoms, or also to generate arbitrary potentials in which the atoms can tunnel around. And in particular, this talk, I will focus on how we do this order. And well, this can, by using the DMD in an oversampled way and using error diffusion algorithms, which are similar to newspapers in black and white, one can generate such grayscale potential. And it's important to keep in mind that, of course, our objective has a finite resolution. So whatever we program with these well-discrete sites, we have a certain convolution with the nearest neighbors, and hence there will be a bit of correlations with the nearest lattice sites. And a great property of our system is that we're able to interrogate the atoms and know exactly what is the light shift in that individual lattice site. So we do this by just sending them the same light for a series of repetitions, prepare a unit filling multi-insulator, and just via microwave spectroscopy, we are able to tell the amount of intensity in the individual lattice sites, so that we can obtain a histogram of the cycles of the tunings, which essentially is just our disorder distribution, which we characterize with a capital delta, which is a disorder strength, which is nothing but the full width at half maximum. And this then becomes kind of an extra term in our Bose-Hubbard model as a side resolved chemical potential. And well, as I mentioned, we have a finite correlation that does affect our disorder, but as long as it's random, this does not really change too much the physics that we will be observing. And let me also mention that while our interest is going to be on out of equilibrium dynamics, we can also quickly take a look at what happens in equilibrium. So for example, if we start from a superfluid and we introduce slowly in an adiabatic way this disorder, we will just reduce these superfluid peaks, which are usually seen in time of flight as an evidence of superfluidity. And as this has already been shown in some of the experiments that Thierry mentioned today. And if we start from the multi-insulator, we can also see that indeed it melts once the disorder becomes stronger comparable to the interaction strength. And this kind of emergence is similar to the kind of processes that lead to the formation of a Bose glass in the disorder Bose-Hubbard model. But the focus of the talk will be, as I said, out of equilibrium dynamics. And let me now jump into summarizing some of the results that we've obtained. So at zero temperature, this is how our system would look. So it's typically around 200 lattice sites with 200 atoms. And we begin by preparing this system in some easy to recognize density pattern. And for example, a very common one is this charge density wave, which like the experiment Julie already showed yesterday. But in this very first experiment that we performed, we just did the domain wall, which means we remove all the particles on the right part in the system and we look at the dynamics of this initial state. That is, we start at a very deep lattice in which tunneling does not take place. And then after a quench, we go into a shallow lattice in which tunneling is finite, interactions play a role, and additionally we introduce a disorder. And after a certain time of waiting, we take a snapshot of this experiment. Yes, please, Thierry.
Yeah, can I ask a very naive question? You showed us these images where your field of view was much, much bigger, whatever, 50 or 60 by 50, 60. And here you show images where it's mostly 20. Is there a reason for that, or is just convenience to prepare the initial state, or just out of curiosity?
So I don't know, I guess the first pictures you referred to was the thermal cloud, right? Or
yes, exactly, which was
well,
a huge,
the simple
huge
answer,
image.
You were complaining before about the parabolic trap. So it's pretty much that we could, of course, look at the whole system, but we are only able to generate multi-insulators with one atom per lattice site in the very center of the system.
In the center.
And this is only limited by the optical lattices, but not by the field of view of our objective.
Okay, super. Thanks a lot.
Yes. Yeah. So let me see if I can just directly go to where I was. Yes. So as I was saying, this domain wall dynamics after a certain time. Here I'm plotting some of how do these dynamics look for the non-disordered case. This upper row is just individual snapshots, and this is an average over several repetitions. And as you can see, after around 100 tunneling times, while all the particles were started in the left part, essentially they occupy homogeneously this harmonic shape is already the system size, which is given by the harmonic trap. However, when we introduce a very strong disorder in the system, we're able to see something that even after hundreds of tunneling times, there's a depletion in the right side and hence a higher density in the left one. And this is kind of a signature of Manybody localization. And in particular, to quantify this a bit better, we look at the so-called imbalance, which is nothing but the difference between the number of particles in the left and the right part of the system normalized. And we see that for very weak disorders, the imbalance takes around 100 tunneling times and then relaxes to a vanishing value. However, in the presence of strong disorder, a finite imbalance can survive up to hundreds of tunneling times. And we can also look at the fixed time and look at the imbalance as a function of the disorder. And this is what we plot here, the imbalance as a function of the disorder strength. And we did see that around below 5.5J, we don't see any evidence of this localization, but then there's a monotonic increase in the imbalance with the disorder. Additionally, of course, one might ask, well, many of these properties might also be observed for a non-interacting system. So how is this not just Anderson localization? And while we don't have any way of tuning the interactions like phase-back resonances, what we can easily do is just reduce the density of our system such that the role of interactions is strongly reduced. And in particular, we removed like two-thirds of the particles before starting the experiment. And we see then that this critical onset of the imbalance happens at a much smaller disorder strength. So this seems to indicate that the interactions move the disorder strengths to higher values. And in fact, if we just compare with numerics for a non-interacting model, we see that the imbalance very quickly already for quite arbitrarily small disorder strengths increases. So this seems consistent with the effect of interactions in our system together with disorder. Now, having introduced this first experiment that we did, let me mention that our quantum gas microscope allows us to, in principle, start with arbitrary initial states. And here, essentially, I'm just looking at strips of different width. So this is just the charge-sensitive wave case. This is the domain wall. But as you can see, we can make strips of 8, 4, 2 lattice sites or any arbitrary value. And the thing of quantum thermalization is that no matter with which one we start, they will not look the same after very long times, which is kind of this erasure of the initial conditions that we have prepared. However, when we introduce disorder, we expect each one of these patterns to be conserved for quite long times. And what we did is fixing at after 300 tunneling times, we look at the imbalance for all these different states as a function of the disorder strengths. So here, this dark blue data is very similar to the one I just showed in the previous slides, but each one of these different traces corresponds to a different stripe width, where this legend indicates the scale. And what you can see is that while the systems are quite similar, and in fact they have similar energy densities, we need a much stronger disorder strength to obtain a finite imbalance for example, the charge-sensitive wave state. And this is quite intuitive to understand if we think that the imbalance has not the same definition for all these different states. The imbalance is defined according to this initial pattern that we have prepared and looking at the difference between the occupation in the lattice sites. So a way of interpreting this is that by preparing a charge-sensitive wave, we are probing localization length of the system much shorter than when we prepare the domain wall. And while for an arbitrary disorder, so for a disorder of 10J, we already see high imbalance for the domain wall, it might take much higher values to see data for the charge-sensitive wave, which is why it's important when comparing these experiments to keep this in mind. And we can get maybe a bit better understanding of this if we just plot, we find at which threshold disorder do we reach the value of imbalance 0.2, which is just chosen arbitrarily for each one of these different initial states. And if we plot the stripe width in the vertical axis and this threshold disorder in the x-axis, we see that as we increase the disorder, the disorder strength needed to localize in the stripe width of 1 is indeed much larger. And yeah. So now let me continue with a different story after showing kind of what we can do with these different probes, which is that of a quantum bath. And the idea of copying many-body localization to a bath is not new at all. And from my point of view as an experimentalist, of course, I know that my system is not really isolated. It will always have a finite coupling to the environment. And this coupling generally will restore ergodicity in the system. So that's why it would be very important to characterize the sources of this coupling and their different effects. And in this sense, introducing a well-controlled bath can also help us reveal properties of the system, as this experiment that was done also in the University of Munich, where they look at this Fermi-Hubbard localized system and their impinging photons, which were scattered from the individual atoms. But a very different question is not that of having some kind of universe-like bath connected to our system, but maybe a small bath, one that's just made of few degrees of freedom, and which hence we must take into account the back action from the localized system into this bath, which is something is usually ignored from a thermodynamically large bath. And this is interesting because it also has a lot of overlap with many interesting questions on many-body localization, like the existence of many-body mobility edges, or for example, these special rare low disorder regions. So in fact, there's been a lot of theoretical proposals saying that in the thermodynamic limit in higher dimensions, the existence of random regions which have low disorder and hence look thermal might destabilize through an avalanche process the whole many-body localized phase. And this is commonly set as a challenge to the existence of MBL in higher dimensions. So as we can see, this idea of the finite bath is relevant for a lot of those questions. And we got particularly inspired by this paper of Catherine Hiat and others on many-body localizations in the presence of a small bath. Let me just summarize the idea of this theory paper. They look at a 1D chain of interacting fermions, which they would expect to thermalize. And they prepare another 1D chain, this time with strong disorder, in which they would expect many-body localization. Now they couple these two systems together, and they ask the question, what will be the outcome? And one might think that the system might just globally thermalize because the upper chain behaves as a bath to the lower one. But of course, because of this back action effect that I mentioned at the beginning, it could actually be that this does not happen and that indeed the opposite happens, that the upper chain gets localized via the interactions with the lower chain. And indeed, in this paper, they show that depending on different parameters, they are able to observe both a total thermalization of the system, indicating that the bath efficiently delocalizes the system, or also a full localization of the system, which is commonly called many-body proximity effect. And now, while experimentally it seems a bit challenging to prepare these two different chains coupled to each other, it's easy to realize that this kind of ladder-like system is analogous to a single chain where we have two different species, and that would be a dirty particle component and a clean particle component. So the meaning one that feels the disorder strength, the other one that just sees a clean optical lattice. And it turns out that this is straightforward for us to realize, since the laser that we use for this disorder potential is in the so-called tune-out wavelength of the f = 1 mf - 1 hyperfine state. This means that while the f = 2 mf - 2 will feel this kind of disorder potential, the f = 1 will essentially just experience a vanishing potential. And from now on, instead of talking about hyperfine states, I will just refer to this one as the dirty component and to this one as the clean component. Now, we can already see, as it's quite intuitive, that if we prepare a charge density wave initially, but independently, so with all the particles in the dirty component or all the particles in the clean component, in the dirty case, this charge density wave pattern seems to remain even after many tunneling times. The clean component already after pretty much 3 tunneling times has already erased this initial pattern. So they indeed are extremely behaving in a very different way. But we're not interested of looking at them individually, but rather to prepare a mixture of these two different hyperfine states and look at how they affect their respective dynamics. And this will be described by this seemingly more complicated extended Bose-Hubbard model, but it's actually quite simple if one takes into account that we are working in a regime where interactions between the two species are essentially the same as the interactions between each one of the individual species. So there is a single U term ruling this whole dynamics. And we are in a situation where before the disorder is kind of close to an SU2 symmetry of the states. And these will be the parameters at which we'll be working. We will be working in all the experiments with the same J, U, and a quite strong disorder, which of course only affects the dirty state. So again, let me show this intuitive schematic of our atoms. Now we prepare this charge density wave. And first, let's again just focus on the dynamics of only all the particles in the dirty state. And this is how the imbalance dynamics looks like. So I'm plotting up to more than 1,000 tunneling times the behavior of the imbalance. And what we essentially see, like in most of these experiments, is that the imbalance monotonically decreases, but at some time scale essentially remains finite even after very, very long times, in which at least seems a steady state value. Now, if we look actually, this can be nicely parameterized by just making a sum of 2 different exponentials with an offset. And this gives us an initial time scale, which is a bit hard to see, but in the very short dynamics, which is of around 1 tunneling time, and a second one which is 2 orders of magnitude larger. So this can be explained by the particles at the beginning just tunneling into empty sites, so interactions play no role in this initial timescale, while when interactions start to become relevant and doubly occupied sites are formed, we have this second much lower timescale. And while I just seem to suggest that this offset would kind of live forever, with our data we can of course just give an estimate on how slow would it have to be this kind of decay of the imbalance based on what we can measure. And we can estimate that any kind of decay at longer times has to happen in a time scale well above 2000 tunneling times. And again, just to show, take a look at the short time dynamics. We see indeed these 2 different time scales I was mentioning before. And we also see an interesting fast formation of doublons. So initially we have a state with no doublons, but then very quickly, a lot of particles with doubly occupied sites will appear. And this is a consequence of both having interactions and disorder together. Now, having seen the dynamics for this purely dirty state, now let's introduce some of these clean particles, which we can do just via microwave pulse. And let's look at the dynamics mainly of the dirty particles. So we're gonna just be looking at the imbalance of the dirty particles. We can do a spin selective measurement to see the effect of the interaction between the 2 of them. And I will be focusing on the longer timescales. So I will ignore these initial 50 timescales, timescale of 50 tunneling times. And I will be plotting the imbalance in a logarithmic scale to be able to better see any kind of delocalization phenomenon. And again, this PC equals 0% just is the same data I was showing you before, so where there's no particles in the clean state. Now let's begin and see what happens when 70% of the particles are transferred to the clean state. And what we see is that indeed there is a quick delocalization of the system, reaching an imbalance that it's at least compatible with a finite, with a 0 imbalance within our statistical relevance. If we look at 30%, we see a quite similar behavior. Indeed, the timescale is a bit longer, but we also see a delocalization of the system. But notice that also, it seems also compatible with a fit where we have an exponential with an offset, as I was doing before. And if we actually go to much smaller sizes of so really the limit of a quantum bath, it's not so clear the behavior. So while again, we can also only say what happens up to 1000 tunneling times, it seems like the imbalance does not vanish. So there is not a full delocalization of the system within this time scale. And it seems that a fit of just a single exponential would indeed not be compatible, but this exponential with an offset is a better description. So this might even mean that indeed Manybody localization can survive in the presence of a small enough bath, which would be consistent with some of the results of this theory paper I mentioned, or it could just be that the timescales get pushed to such long timescales that are well above what we can distinguish with our experiment. Now,
3 minutes, 3 minutes.
Yes, okay. So we can also look at the clean component, and we see then that essentially the imbalance just quickly relaxes to 0. So there seems to be at least no evidence of a localization via interactions of the clean component. So while this might seem to indicate that there is no effect of this proximity effect in which the Manybody localized system localizes the clean particles, it could also just be that the length scale in which this localization happens is way longer than what we can probe with this charged to wave pattern. So now let me essentially conclude.
Yes.
As a summary, we have observed signatures of MBL in a 2D Bose-Hubbard system. We have probed different initial patterns which lead to different length scales being studied. We realized a mixture with clean and dirty particles, and we were able to see that while with a large quantum bath we can delocalize the system, finite imbalance seems to remain for very long time scales for a small bath. And let me now describe some of the ideas we have in the outlook. So first one would just be try to explore more this interaction-induced localization. We could, for example, instead of prepare some initial charge density wave, prepare the particles in some disordered looking potential and freeze them by using this this spin-dependent potential, so that we can see the effect of that the interactions can do on the clean particles and whether they can lead to a localization. Another one is explore directly these low disorder regions that I mentioned at the beginning by just making a hole in our disorder potential that we prepare. However, it seems like the timescales for this kind of avalanche processes might be well beyond what's probable in any experimental system. So far, we have not been able to observe anything there. And another one is comparing quasi-periodic versus random potentials, which should be able to be done in our setup in one-dimensional systems. Last, let me just mention that we're working hard in an outlook, also improving our setup. And recently we're fighting against this parabolic trap and trying to make homogeneous systems well above 50 times 50 lattice size, so around 2,000, more than 2,000 atoms. And also we have been able to explore timescales well above 3,000 tunneling times, which are all very interesting ideas to explore MBL in the future. And in particular will allow us to look not only at 2D, but also at 1D and maybe scale the system size. So with this, let me just thank the rest of the team, particularly Jae-Yoon Choi, postdoc, and Sebastian Hill, PhD, which many years ago started this direction of MBL, and also Theory, David Hughes and Betty Kakamani, their support, and the more recent team, which is working now on upgrading our setup. So with this, I'd like to thank you for your attention. Okay, thank you very much. I'm looking for questions okay, Nicolas Cherore has a question. Thierry Jamarki has a question. Okay, let's start with Nicolas Cherore.
Hello, thank you for the talk. Actually, my question is related to one of your last slides. So one of the usual problem of the numerics is that the MBL transition is broadened because you don't have enough particles. But here you are in 2D, so even with 200 atoms, I guess that you are much larger than in the numerical simulations. Did you try to take the time to investigate a bit the critical properties of the transition to take advantage of your quantum simulator? Or not? Or is it not sufficient, 200 atoms? Well, I could say in terms of this critical behavior, and it depends what kind of observable you're looking for, but these results that I showed for the domain wall and also for all these different things is pretty much the farthest we have gone into just looking at the phase transition, just estimating at which disorder strength do we see this onset of the imbalance. And at least, I mean, I don't know what you have in mind, but of course, it would be very exciting. Exponents or, I don't know, scaling analysis. No, this is, well, yeah, we did look at some kind of exponents of the, well, in our first paper, at least we tried to estimate from the decaying density in the domain wall to fit at least kind of localization length as a function of the disorder. But I don't think we tried to extract anything like a critical exponent or something like that. I'm not sure if this is in general, I think the system size might already be interesting to explore such things. It's just that I'm not sure what's the best property to look at to extract these exponents close to the phase transition. And I guess we also need a very good control of the disorder strength and certainty in that regime. Okay, thanks. So, yeah. Okay, Thierry.
Yes, thank you. First, thanks for the talk, which was a very beautiful talk. The
yes,
second, one thing you could perhaps compare to, since you were mentioning that you don't know whether it's an effect of finite size or for equilibrium system, there are very efficient numerical calculations. Even in 2D, there are papers by Prokofiev, Matthias Troyer and company, which could at least tell you whether the localization scale for the equilibrium system is much larger or much smaller than the size of your system. If it's much larger in equilibrium, you're probably dead. I mean, you will not make the difference. If it's much smaller, then you're probably at least in good shape to worry about the effects of disorder. So the question was, did you compare with that, or do you have an idea what already in equilibrium the localization scale of a 2D system would be compared to your sizes? But this will depend, of course, of the strength of the disorder. Right? So yes, for very large disorder strength, we're quite convinced, of course, these effects become very small. And when we have a finite imbalance with the charge density wave, we know that the length scale, at least experimentally, has to be on the order of few lattice sites. Okay. I do not have looked at the direct comparison with
equilibrium simulation. So you would essentially...
The reason I'm raising this is that in 1D, roughly what you say would be correct. In 2D, when you look at the numbers they got, it's getting insane. Bosons are insanely resistant to disorder in 2D and then in 3D. So I think it could be interesting to look at the numbers. Again, I don't have the numbers in my head. You know, already for fermions or for free particle, the localization lengths become exponentially large in exponential of KFL in 2D. So this, what I mean is that at least numerically, the localization lengths could be quite large. So it's definitely worth making sure you're in the right limit. But as you said, if the disorder is large, there is no question that the localization lengths will become ultimately short enough that you. But this could be pretty large disorder, actually.
Yeah, okay, no, this could be interesting. Of course, the interaction strength might also play a bit of a role. We are quite close. So in the non-interacting limit, we're essentially hardcore bosons in the sense that interactions are much larger. So I don't know also if that makes an effect. I believe that if we're able to make U very strong and J very small, for example, we could describe still our system like, just like a 2D hardcore boson system. And then, for example, I also don't know if this behavior will... So interactions might have very different behavior, I guess, for this in our system.
Okay.
Thank you.
Well, I think we can stop for 5 minutes for another coffee. Thank you very much, Antonio. It was really very nice, very interesting. I had a couple of questions, but I think it's wiser to shut up and let people go and relax for 5 minutes. Okay. Thank you very much.